In the last video, we constructed a Prufer code from a given labeled tree, and we looked at an algorithm that'll do this for any given tree, labeled tree. In this video, we'll look at an algorithm for taking a Prufer code and producing a tree whose Prufer code is this given sequence. So let's take a look at this algorithm. This is algorithm 3.22 from the text. So here we're given as input an integer n greater than or equal to 3, the set of labels that we'll be using, so 1 through n, and we're given a sequence. This is the Prufer code, the sequence a1 through an minus 2, where each member of the sequence is from this set 1 through n. And we'll take this given information and produce a graph. We'll have to prove it's a tree, a graph with this vertex set. So a labeled graph with this vertex set. All right, so again, we start with a loop from I between 1 to n minus 2. And in each instance of the loop, we're going to perform 3 tasks, and then we'll increase I by 1 and perform the loop again until we get to n minus 2. And then we'll have 1 task to do here to give us our final edge, and eventually we'll output the edge set of the tree. In particular, we're going to output the tree. Okay. So we're given this sequence, little s1, 1, 2, 3, 4, 5, 6. It's order 6. And so my n here is 2 more than that. My n here is 8. And so the tree that we're going to be outputting will have order 8 and labels coming from this set big S1, which is the integers 1 through 8. All right. So let's analyze the algorithm. What do we do? So we're starting with I equal 1 here. And we're going to look for the smallest element of big S1 that doesn't appear in little s1. And then we're going to make the edge, E1, between those 2 vertices. So here I have my vertices all laid out. I'm going to look at big S1 and look for what's the smallest label that does not appear in little s1. Well, 1 and 2 appear in little s1. So my smallest label not appearing in little s1 is 3. And so I'm going to make an edge between 3 and the first term of this sequence. So 1, 3, so E1 would be the edge, I guess I'll use a set here, would be the edge 1, 3. So I'm just going to draw an edge between 1 and 3. And then what do? We let big S2, we remove 3 from it and make that be big S2. And we also remove the first term of the sequence, right? This would be A sub 2. So in the next instance of this loop, I'd be looking at little s2, which would be 8, 1, 5, 2, 5. And my big S2, I delete 3 from this one, so it would be 1, 2, 4, 5, 6, 7, 8. And I'll repeat the same process. I'll look for the smallest element here that doesn't appear in little s2. So let's see, 1 and 2 still appear here. So it looks like my smallest one is 4. And I'll make that adjacent to vertex 8. So edge 2 is going to be 4, 8. So 1 and 3 were adjacent from the other one, and now I'm making 4 and 8 an edge. And then we'll delete 4 from big S2 and remove this first term from little s2. So that is S3 now. 1, 5, 2, 5. And big S3, we're going to delete 4 from it. So 1, 2, 5, 6, 7, 8. And we'll do the same thing. 1 and 2 still appear in little s3. So, oh, and 5 appears there. So the smallest label of big S3 not appearing in little s3 is 6. So my edge E3 will be 6, 1. So let's see, 4 and 8 were adjacent from before, 1 and 3 were adjacent from before, and now I'm doing 1, 6 is my next edge. And we repeat the same process. So now S4, little s4, is 5, 2, 5. Big S4 is 1, 2, 5, 7, and 8. And I repeat the process. So now, let's see, to find E4, smallest label of this not appearing in this. Well, now 1 is not in little s4. So 1 is my smallest label. So I'll make that adjacent to 5. So 1, 5. My next one, we know 1, 3 is adjacent from before, 4, 8 is adjacent from before, and what, 1, 6 was adjacent from before. So now 1 and 5 are going to be adjacent. All right, repeat the process. My little s5 now is going to be 2, 5. And big S5 is 2, 5, 7, 8. And we repeat the process. So now my E5, my smallest label here is 7. That doesn't appear here. So 7 and 2 will be my edge. So 2, 7, 2, 7. Let's see, we have 4, 8 from before. We have 1, 6 from before. We have 1, 3, and 1, 5 from before. Yeah, 1, 5 from before. And repeat the process. Now, I'm just doing this for illustrative purposes. If I'm actually doing this myself, I won't make a new tree for each instance of this loop. I'll just keep the same vertex set and just build on it over time. But this just works easier for recording. So little s6 will just be the sequence 5, right? I used 2 from the last one. And s6, big S6, will be 2, 5, 8. So now 2 no longer, E6. So now 2 no longer appears in here, and so my edge is going to be 2, 5, 2, 5, 2, 5. I got to remember all my edges. 1, 3, 1, 5 was an edge. 4, 8 was an edge. 1, 6 was an edge. 1 more. 2, 7 was also an edge. Wait, that was weird. I swear I just drew 2, 7. There, 2, 7 is an edge. And so now I have, my n was 8, and so I'm done with the loop. And so my very last step, so let's see what we've done now with this algorithm. I've now completed this loop. And now I take the last 2 elements in S sub 7, and make those 2 adjacent. Right, so now my big S7 will just be 5 and 8, and now I'll just make those 2 adjacent. So E7 is going to be the edge 5, 8. So 5 and 8, that's an edge. I have 4 and 8. I have 2, 7. We have 2, 5, 1, 5, 1, 3, 1, 6. I think that's all of the edges. And so here's my resulting tree, and I can record its edge set. One thing I'll do here is I'm just going to redraw this a little bit so it looks kind of nice, looks nicer. So here I have my vertex 1. It's adjacent to 3 leaves. How about 3? And now how about 6? 6 and 3. 1. Let's see, 1 is adjacent to 5 as well, and then 5 is adjacent to 2, which is adjacent to 7. 2, 7. And then 5 is also adjacent to 8, which is adjacent to 4. So 8, 4. And if you'll notice, this is the same tree that we started with from the last algorithm. Right, we get that tree as our output. And this is the tree we started with the last one. And so at least we're seeing an instance here that this pair of algorithms are inverses from each other, right? Sorry, it's lagging. I outputted this Prufer code, and then we took that Prufer code and produced the same tree that we started with. So these algorithms, well, this is what we need to prove now, is that these algorithms undo each other. So what each of these algorithms establishes is a function from the set of distinct labeled trees to the sequences of length n-2 using the same labels. And the other algorithm hopefully establishes the inverse of that function. So this is what we need to prove, is that those two functions are inverses of each other. That'll establish our bijective correspondence between the set of distinct labeled trees and these sequences. And then it's a much easier job to count the sequences, and we'll know that the number of distinct labeled trees is n to the n-2. So join me in the final video of this little 4-part video series where we will finally prove Cayley's tree formula. See you there.